So to just convey these ideas and also like to correlate what we have learned, like let me take an example and then like we would discuss a few points. Okay. So let me take an example of a typical mass spring damper system that all of us are familiar with. Let us say I have a mass, this is a 1 degree of freedom mechanical system. So let us say like I have a mass m, okay, which is connected to a spring, linear spring with a spring constant of k and a linear damper with a damping coefficient of c, okay. And let us say I apply a force f of t on this particular mass, and the displacement of this mass from its equilibrium position, let us call it as x of t. So all of us know that the governing equation of motion for this system is going to be, of course we derive it based on the Newton's second law of motion, right. So the governing equation of motion for the mass spring damper system is essentially mx double dot plus cx dot plus kx is equal to f of t, okay. Of course in this particular course, if I use a dot over a variable, that means I am taking its time derivative, okay. So x dot means it is the first time derivative of x of t, x double dot t means like it is the second derivative of x of t with respect to time and so on, okay. So if we, this is the governing equation for this mass spring damper system. So as we know, like mx double dot like characterizes the inertia effects that occur in the system. Cx dot essentially correspond to the viscous dissipation that happens due to the presence of a damper, right. The viscous terms, the dissipation terms are modeled using Cx dot. Kx essentially is indicator of the compliance, right, that is present in the system, alright. So these are essentially typically used to visualize this what to say class of mass spring damper systems, and even like one would use these analogies to develop models for even other systems from other domains, okay. So but let us consider this what to say example, right, and we immediately realized that the governing equation is a second order, let me just come up, okay, is a second order linear inhomogeneous ordinary differential equation with constant coefficients. Okay. So we can see that the order of the system is 2 because we have a second order derivative in the governing equation. It is linear as is evident from the governing equation because the equation is linear in x of t and f of t. It is inhomogeneous because like we have a forcing term on the right hand side of this ordinary differential equation, and it has constant coefficient, like that is reflective of the system being time invariant, right. So this is an LTI system, okay. So this is essentially an LTI causal single input single output system, okay. The class of systems that that we are essentially looking at. So if we look at the response of the system, we are going to revisit these concepts in detail later, but if you look at the system response, we are going to have two components. One due to the presence of any potential non-zero initial conditions, okay. So for example, like I can displace the mass a little bit and then leave it, right. So then I am giving a non-zero displacement as an initial condition, right. So this would be called as the free response. These are terms which we will define later on, okay. And then we can also have a system response due to the input provided. In this case the force is the input to the system. So in fact, like if we want to visualize this using the typical systems perspective. So in this case, the mass spring damper system, the input is the force F of t, the output is the displacement, right, displacement x of t. So in other words, like if based on the input that is provided or the force that is provided, I can have a displacement, right. So that essentially comes as what is called as a force response of the system. So the system response can have two components, right, and this is an example of a linear time invariant causal SISO system. On the other hand, let us say we consider a scenario where the spring constant changes with time. Could happen. So for example, like if I keep on operating the system for a long time, the spring may weaken, right. So then the spring constant may change with time, right. So let us consider a scenario where the spring constant changes with time. Then the governing equation could be rewritten as mx double dot plus cx dot, okay, plus kt x of t is equal to f of t. So this kt, okay, is now representative of a time varying spring constant, right. A time varying parameter comes in the system model. So as a result, this becomes what is called as a linear time varying system. So this is just an example of when we could potentially get a linear time varying system, okay, instead of a linear time invariant system, okay. So that is a linear time varying system, okay, and we can immediately realize that the governing equation in this case is once again a second order linear linear inhomogeneous ordinary differential equation, but with time varying coefficients, okay. So that is the class of equations that typically would be used to characterize linear time varying systems, okay. So we will have time varying coefficients in the governing equation, okay. So that is something which will which would come into play. So now let us consider another example. Let us consider another scenario where the spring is non-linear. This also could be a potential scenario which can be encountered in practice. So what do we mean by this, right? So essentially in many problems in practice, like if we have a, let us say, a coil spring, right, in let us say in some machine element, or let us say even in our automotive suspensions, right, we take a spring and then like we test it by essentially giving a force and then like plotting the force displacement characteristics. So by and large what may happen is that we may get a curve which may be non-linear, like if we test it in the entire domain, okay. So what typically happens is the following, like see, even let us say we take a car suspension where we have a coil spring which is compressed initially, or even if this is more evident, let us say in a two-wheeler, you would have seen a coil spring, which essentially deflects as the two-wheeler is going. So essentially let us say we have the spring in an initial state of compression, right. So let us say that is the initial compression that we have essentially given. Let us call this displacement as xi, and by and large what we have is that we would operate the spring in a region around this xi, by and large, like so it may so happen that the spring may be operated in a region around this initial state, most of the time. Then we can immediately observe that in this region the spring can be approximated as a linear element. So then the question that we can ask ourselves is the following, right. Given this range of operation of the spring, can I use a linear approximation to model the process? Okay. Then if yes, I could use a linearized model, and then like we can go to the class of linear time invariant systems. But on the other hand, let us say like I am in a situation or I am in an application where the spring is stretched and compressed over a wide range of displacements. Then I may no longer be able to use a linear model for the spring. Then what is it that I can do? So in such cases, the governing equation would become, okay, may be written as, right. I am just taking an example where let us say the governing equation for the spring's response is a quadratic function of the displacement, right. So let us say what will happen is that the governing equation for this mass spring damper system will then become mx double dot plus cx dot plus let us say kx squared t is equal to f of t. Okay. So you see that the term kx squared t makes the system non-linear. Okay. So this becomes a non-linear system, okay, once we have such a response, and we could immediately observe that this is still a second order ODE, but now it becomes a non-linear ODE, right. So non-linear inhomogeneous ODE with constant coefficients, right. So that is what happens to this governing equation. Okay. So we are just considering different examples to just learn like how the governing equations would change depending on the scenario. This is just to get a broad idea about the class of systems that we are studying. Okay. So I hope just through the simple example, the difference between linear or non-linear systems and time invariant, time varying systems have become a little bit clear, and we just consider a simple example to show how these attributes are reflected in the governing equations of such systems. Okay. So to conclude this sesh class, let me just show you some simple examples, this just simple simulation results, just to convey the concepts what we have learned. So let us consider the mass spring damper system that we have been looking at. Let us say like I consider these following parameters. Okay. So that is like I consider the mass of the element to be 1 kilogram, right, the damping coefficient to be 0.5 Newton second per meter, and the spring constant to be 0.75 Newton per meter. Okay. I am just taking some values to just solve those equations, right. So let us say that we provide a force input of 1 Newton, okay, at time t equals 0. Okay. So if we solve this mass spring damper system, so as we have already discussed, like we can have what is called as free response of the system. That is, we can have non-zero initial conditions and we have what is called as a free response, which is essentially indicated by this blue curve, right. We can see that the initial displacement is at 1 and then like it essentially oscillates and then goes to 0 finally. Okay. On the other hand, I can have a 0 initial condition and then like give a what to say input to the system, which essentially is what is called as a forced response, right. So, that is the response term due to the input that we provide, and that is essentially denoted by the red curve, okay. So, which essentially goes and settles down at some non-zero finite value, okay. So, if we combine both, that is we give a non-zero initial condition and the input, we get the curve which is indicated in black. So, we can see that the response is the sum of both contributions, that is the free response plus the forced response term gives the third response, right, where we have a response from the mass spring damper system that consists of both the non-zero initial condition component and the force input component, right. So, once again please remember, like what was our system? For us the mass spring damper system was visualized as one to which we give the force as the input and the displacement is the output, okay. That is why we are essentially plotting the displacement and studying it, okay. Yeah. So, this is just to show what to say, whatever we have learnt through a graphical visualization, okay. So, let us now look at time variance, like how in the previous case the model was linear time invariant, okay. So, the system was linear time invariant, the model was a linear ODE with constant coefficient. Now, let us say instead of having a constant spring constant of 0.75 Newton per meter, let us say the spring has a varying time varying spring constant, which is of this form 0.75 e power minus 0.001 t, okay, Newton per meter, okay. So, the spring constant is slowly decreasing from the initial value of 0.75, right. So, if we plot it, like of course, we can see that I have just zoomed into a range of 0 to 100 seconds. So, maybe around the 75th second we can see that the spring constant has what to say decreased to around 0.693 Newton per meter, okay. So, that is what has happened. So, and as we just discussed a few minutes back, the governing equation now becomes mx double dot plus cx dot plus k Tx of t. So, this makes it as a linear time varying system, okay. So, we can see that the system is now become LTV, right, due to this time varying spring constant. So, let us see what is the effect of this on the system response. So, we consider 0 initial conditions, right. So, let us not worry about the free response, we only look at the force response here. So, what we do is that we are giving a unit step force, a force input of 1 Newton in one scenario at 0 seconds time t equals 0, which is the response is indicated by the blue curve. And then what we do is that we then give the same in the next scenario, we give the same unit step force input, okay, at a time instant of 75. So, as we realized from the previous slide, at time t equals 75 seconds the spring constant anyway has decreased, right. So, because it is a time varying parameter in this particular case. So, you could immediately see that the response which is plotted by the red curve is different from the blue curve, right, which is essentially going against the definition of time invariance. So, if you recall that definition of time invariance, if we give the same input at let us say time t equals 0 and time t equals 75 as in this example, I should get the same output, right, but that is not the case. Why? Because we have a time varying system, okay. So, we can immediately see that the red curve is different from the blue curve, right. So, you can see the peak of these oscillations, like that has increased in the red curve when compared to the blue curve, right. So, in a certain sense, like the responses are becoming different, okay. So, this gives us an overview of how these factors affect the system response, just through simple example, like I just wanted to communicate how linearity, time invariance and all come into play, Okay. So, we would stop here. So, we have essentially looked at a big picture viewpoint view of what we are going to essentially learn in this particular course, and defined a few terms in this particular class, and then like looked at an example. That is what we have done here. And we also looked at what is meant by sensor dynamics, actuator dynamics, okay, and unity, non-unity feedback and so on, right. So, in this particular class. So, in the next class we would essentially meet and start off with mathematical preliminaries, and we would revise mathematical tools that we would be using in this particular course. Okay. Thank you for your attention.